If you want to understand how the ancient Egyptians really cut granite, forget the fantasy of secret machines and lost industrial saws. The truth is harder, slower, and in many ways more impressive. Granite is one of the toughest stones the Egyptians ever worked. Copper is far softer than granite, and yet the evidence from quarries, tomb scenes, drill cores, saw marks, and experimental archaeology all points in the same direction. They did not defeat granite with one miraculous invention. They broke it down with systems, patience, abrasive power, and above all, for the first brutal stage of quarrying, a dark, dense hammerstone called dolerite. That matters because granite sits at the center of one of ancient Egypt's biggest engineering mysteries. It was used for sarcophagi, obelisks, temple elements, colossal statues, and some of the most symbolically important architectural pieces in the royal landscape. At Giza, granite appears in the king's chamber, in portcullis blocks, and in monumental internal elements that had to be quarried, shaped, moved, and fitted with astonishing control. In later periods, red and pink granite from Aswan became almost a royal signature, chosen not because it was easy, but because it was durable, prestigious, and visually powerful. And that is exactly why the question has fascinated people for generations. How do you cut a stone made mostly of minerals that are themselves extremely resistant to wear? Granite is not some impossible supermaterial, but it is hard enough to expose every weakness in a toolkit. Quartz inside granite ranks about 7 on the Mohs scale, feldspars around 6, while pure copper sits far below that. So if you imagine the Egyptians simply pushing a copper blade through granite the way a kitchen knife slides through fruit, the whole thing sounds absurd. But that mental picture is wrong from the start. The Egyptians were not trying to make copper overpower granite. In many cases, they used copper as a carrier, a frame, or a delivery system for something else. The actual cutting was often done by abrasive particles, especially sand-rich and hard quartz, ground between tool and stone. And before any fine cutting began, the stone itself often had to be attacked in a completely different way, not by slicing, but by pounding. That is where the surviving evidence from Aswan becomes decisive. At Aswan, the great granite quarrying region of ancient Egypt, archaeologists and surveyors have found the landscape of production still written into the rock. There are abandoned blocks, channels, scars in the bedrock, quarry roads, spoil heaps, inscriptions, and most importantly, large numbers of battered stone pounders. These were not decorative objects and not ritual curiosities. They were work tools, usually OF dolerite, a very tough igneous rock that could survive repeated heavy impacts better than softer stones. When you stand in front of the unfinished obelisk at Aswan and look at the trenches around it, the quarry still preserves the logic of the method. That unfinished monument is one of the clearest pieces of evidence in all of Egyptian stoneworking. It was never removed from the bedrock, so the extraction process stopped midstream and left behind its own negative. The long channels cut around the obelisk do not look like the smooth kerfs of a modern-powered saw. They look pounded. Their surfaces are rough, pecked, and bruised. For decades, scholars connected those marks with the masses of dolerite pounders found in the quarry, concluding that ancient workers hammered out the channels by repeated blows, gradually isolating the obelisk from the living rock. Whether every stage was done by pounding alone remains debated, but no serious reconstruction of pharaonic granite quarrying can ignore the central role of those hammerstones. This is where the title's promise about hieroglyphs needs a careful correction. Hieroglyphic inscriptions and painted scenes are incredibly valuable, but they do not function like modern engineering manuals. They rarely give a clean, step-by-step technical explanation saying, first use this tool, then apply this abrasive, then rotate at this angle. What they do provide is context. Quarry inscriptions mark teams, places, and royal projects. Tomb scenes show workshops, craft organization, stone transport, and the making of statues. They reveal the human system around the work, while the quarry marks and tool traces reveal the mechanics. One of the most useful visual sources comes from the tomb of Rekhmir, the great 18th dynasty vizier at Thebes. The scenes there are later than the age of the Great Pyramid, so they cannot be treated as a direct Old Kingdom instruction sheet, but they matter because they show how Egyptian elites wanted royal production to be represented, organized, specialized, supervised, and labor-intensive. In Rekhmir's tomb, sculptors haul stone and work on colossal royal statues as part of a broader sequence of temple industries. The message is unmistakable. Monumental stoneworking was not some mysterious event outside the normal economy of the state. It was a managed craft process carried out by skilled teams under official oversight. That is a crucial point because one of the most misleading modern habits is to isolate the finished object from the labor system that made it possible. People stare at a granite sarcophagus or a polished statue and imagine a single secret tool. The Egyptians thought in chains of work. First came quarrymen, then transport crews, then rough shapers, then drillers, sawyers, polishers, carvers, and finishers. Scribes recorded deliveries. Overseers managed labor. Carpenters made handles, sledges, and rigging. Metalworkers maintained blades and drill tubes. The technology was real, but it was distributed across people, materials, and time. So what exactly did the dolerite pounder do? In simple terms, it was the heavy hitter of granite quarrying. Workers swung or dropped these hard stone pounders against the quarry, face again and again, crushing crystals at the surface, bruising the rock, and gradually creating pits, channels, and trenches. This was not elegant work. It was repetitive, noisy, physically punishing labor. But it was effective. If you're not trying to shave off clean ribbons of stone, but instead to open a trench around a block or rough out a form, impact is your friend. Dolerite was not magically sharper than granite. It was tough enough to survive repeated pounding and hard enough to damage the stone under sustained force. And that helps explain why so many pounders are found at granite quarry sites. They were consumed by the process. Repeated impact battered them, broke them, and left fragments scattered across working areas. Survey work in the Aswan region has documented dolerite tools and fragments in association with quarry faces, debris, and extraction zones. In some places, hieroglyphic inscriptions on quarry faces may even have marked teams or work areas. The landscape itself becomes a record of organized labor. Inscription here, channel there, broken pounders everywhere, all tied to the same industrial logic. Now, it would be misleading to say the case is closed on every detail. Some more recent archaeological work at Aswan has reported charcoal, ash, and burned mud brick in quarry contexts, raising the possibility that heat played a role in at least some stages of extraction. This has revived discussion of fire setting or thermal assistance, a technique known in other ancient mining traditions, where heating and cooling rock can help weaken it. But this evidence should be handled cautiously. It does not erase the clear importance of dolerite pounders, and it does not prove that fire was the primary method for all pharaonic granite quarrying. The safest conclusion is that pounding is firmly attested, while the role of heat in some contexts remains plausible but still debated. Once a block or preform had been isolated, the next challenge was shaping it more precisely. Here, the toolkit changes. The stone pounder remains useful for roughing out, but if you need a straighter cut, a drilled hole, or a flatter surface, percussion alone is not enough. This is where copper saws and drills enter the story, and where modern confusion often gets worse. People hear copper saw and immediately dismiss it because copper is softer than granite. But the copper blade was not expected to bite into the granite by edge hardness alone. In abrasive cutting, the blade can serve mainly to hold and press the abrasive, while the abrasive grains do the grinding. Experimental archaeologist Dennis Stocks spent years reconstructing this principle with ancient-style tools. In widely cited experiments, he and collaborators showed that granite can indeed be sawn with a toothless copper blade when sand is introduced into the groove. Now, the sand, especially quartz-rich desert sand, acts as the real cutter. As the blade moves back and forth, its weight and motion force those hard particles against the granite, grinding a channel into the stone. It is slow, it requires persistence and labor, but slowness is not failure. In the ancient world, if a method was controllable, repeatable, and supported by abundant manpower, it was a viable technology. The same logic applies to drilling. Ancient Egyptian stone vessels, statue details, and monumental stone elements preserve drill holes and drill cores that have long been at the center of technical debates. One of the classic disputes was between scholars who argued for loose abrasive slurries and those who argued for fixed hardpoints set into tubular drills. The reason the debate lasted so long is that the tool marks are subtle. Some granite cores show spiral or concentric striations that seem surprisingly regular. And for generations, people argued over what kind of contact between tool, abrasive, and stone could have produced them. A careful study published through the Penn Museum revisited some of that evidence by examining drill holes and cores from Egyptian hard stone work. The researchers compared earlier arguments and ran their own experiments using copper rods and tubes with different abrasives. Their conclusion did not support fantasies of impossible machinery. Instead, it suggested that tubular copper drills used with abrasive slurries remain a plausible explanation, while also showing that the exact choice of abrasive matters enormously. In other words, the mystery is not whether Egyptians could drill granite. They clearly did. The real question is which abrasive recipes and tool setups they used in different periods and contexts. That distinction matters because sand is not one perfectly uniform substance. Ordinary quartz sand can abrade granite, especially with enough time and pressure, because quartz is as hard as the hardest major mineral in granite. But some evidence suggests that Egyptian craftsmen may sometimes have asymmetry. Analysis by the Metropolitan Museum of Art on residue preserved in an ancient drill hole from Amarna identified a corundum-rich abrasive mixture. Corundum is much harder than quartz. That does not mean every Old Kingdom mason at Giza was drilling with corundum every day. The Amarna evidence belongs to a different context and period. But it does prove that at least some Egyptian craftspeople used exceptionally hard abrasive materials when the task demanded it. That is one of the most important corrections to simplistic reconstructions. There was not a single universal method for all granite work across 3,000 years of Egyptian history. Quarrying an obelisk from bedrock at Aswan was not the same operation as hollowing a stone vessel, drilling a sarcophagus lid, smoothing a statue face, or polishing a hieroglyphic inscription panel. Different tasks favored different combinations of pounding, sawing, drilling, pecking, rubbing, and polishing. The evidence makes much more sense when we stop looking for one miracle tool and start looking for a toolkit adapted to stages of production. Still, if you force the question and ask which tool they relied on most heavily at the granite quarry itself, the answer is not a copper saw. It is the dolerite pounder. Copper saws are crucial for understanding fine shaping and long straight cuts. Copper tubular drills are crucial for understanding holes and cores. Abrasive pastes are crucial for finishing and polish. But the first great act of conquest, separating workable granite from the mountain and roughing it into form, belongs above all to heavy stone impact tools. This becomes even clearer when you think about scale. A huge obelisk or a massive architectural block begins life as bedrock. Before you can polish anything, before you can cut a neat slot, before you can carve a sign or a face, you have to win the mass from the quarry. At that stage, the challenge is not elegance, it is volume. You need channels, clearance, and space. You need to control fractures and preserve the integrity of the intended block. Pounding is brutally well suited to that. It allows workers to work gradually around a form, following lines marked on the stone and deepening trenches by concentrated labor rather than by high-temperature metal edges they did not possess. After rough extraction came another kind of intelligence, geometric control. Egyptian stoneworkers had to maintain symmetry, flatness, and intended dimensions over large surfaces. That is why pounding alone cannot explain the final result of many granite pieces. Sawing, rubbing, drilling, and polishing entered the process to regularize surfaces and details. Stocks's experiments, along with earlier discussions going back to Flinders, Petrie, and others, show how toothless copper saws can create grooves when charged with abrasive. The blade is not a knife. It is a carrier of pressure and motion. Once you understand that, the whole technological picture becomes less mysterious and more ingenious. And then there is finishing, the phase most viewers underestimate because the surface looks effortless after completion. Fine quartz pastes and abrasive rubbing could transform a pecked or sawn surface into something much smoother. Museum educational resources describing hardstone carving and ancient Egypt note that when sculptors worked very hard materials, they often chipped or pecked a rough form first, then abraded the surface with progressively finer pastes. That sequence is technically sensible. Rough shaping by impact is fast enough to establish form. Abrasion then refines. Finer abrasion produces detail and sheen. What the eye later reads as perfection is often the accumulated result of multiple abrasive stages, not a single cutting event. This is also where some popular arguments collapse under their own assumptions. You will often hear someone say, copper is too soft, therefore the Egyptians could not have cut granite. But that only follows if the copper itself was supposed to do all the cutting. In real stoneworking, soft materials can serve as tool bodies while harder particles provide the actual abrasion. Modern lapidary work uses the same basic logic. Hard grains under pressure wear away stone. The Egyptians did not need a steel age to understand what repeated friction with the right abrasive could do. They needed observation, labor, and a supply chain for tools and grit. Another popular misunderstanding comes from the astonishing precision of some surviving pieces. The straighter the line or smoother the surface, the quicker some people jump to claims of vanished machine tools. But precision is not a magical signature that belongs only to modern industry. Precision can emerge from process control, repeated measurement, patient reworking, and specialist skill. Egyptian craftsmen were not improvising one-off experiments in isolation. They belonged to traditions that lasted centuries. Knowledge was embodied in workshops, in apprenticeship, and in the correction of mistakes. A polished granite sarcophagus is not evidence that someone cheated history. It is evidence that a highly organized civilization was willing to spend enormous energy on permanence. The hieroglyphic and pictorial evidence reinforces that cultural reality. In tomb scenes, craft is dignified through depiction. Labor appears in sequence. Materials are delivered, transformed, inspected, and presented. Statues are not shown as spontaneous marvels. They are made. That is perhaps the deepest revelation in the visual record. The Egyptian state did not hide the fact that monuments came from human work. It celebrated the coordination of that work under royal order. When scenes in the tomb of Rekhmir show stone hauled for colossal statues and artisans at their tasks, they are not giving us a mechanical textbook. They are giving us the social truth behind the stone. The quarry evidence adds the physical truth. Dolerite pounders, extraction scars, trenches, unfinished pieces, quarry inscriptions, transport routes, and debris fields all anchor the artistic scenes in matter. And the analytical studies add a microscopic truth. Drill striations, residues of abrasive and experimental replication show how tool, grit, water, pressure, and motion interacted on the stone surface itself. When these layers of evidence are combined, the story becomes much stronger than any single clue on its own. So, how did the Egyptians really cut granite? They did it in stages. First, they located usable stone, especially in quarries like Aswan. Then they pounded channels and rough forms with dolerite hammerstones, gradually isolating blocks or shaping large masses. Next, for straighter cuts, slots, and detailed shaping, they used copper saws and drills charged with hard abrasive particles, often quartz-based sands, and perhaps, in some cases, harder materials. After that, they refined surfaces by rubbing and polishing with increasingly fine abrasives. And throughout the process, they relied on organized teams, woodwork for handles and sledges, water, labor management, and a culture of craft transmission. That layered explanation is less romantic than the myths, but it is far more extraordinary. Because myths usually solve the problem by importing power from somewhere else. Aliens, lost high technology, secret machines, forgotten civilizations. The real Egyptian solution kept the power on the ground. It came from geologic knowledge, resource access, repetitive labor, smart use of abrasives, and institutional organization. They used the hardness of one mineral against another. They exploited the toughness of dolerite. They let sand do work that copper could never do alone. And they were willing to repeat that work thousands upon thousands of times. Think about what that means at the human level. A granite monument is not just a triumph of design, it is a record of impact. Every trench in a quarry wall stands for blows delivered by workers whose names we mostly do not know. Every sawn groove stands for grit fed into a cut and dragged back and forth until the stone surrendered by fractions of a millimeter. Every drilled cavity stands for rotation, pressure, slurry, and patience. Every polished face stands for long abrasion after the hard victory of extraction was already won. The finished monument conceals its own violence, but the quarries remember it. And that is why the unfinished obelisk is so revealing. It is not a failure in the modern sense. It is a frozen workshop. Because the monument cracked before completion, the production process did not vanish behind a finished surface. It remained exposed. You can still see the trenches. You can still read the negative space of the intended form. You can still connect the scars in the granite to the surviving hammerstones in the archaeological record. Very few ancient monuments explain themselves so honestly. It also reminds us that Egyptian craftsmen were not infallible. Granite was difficult precisely because it could break unpredictably. Cracks could destroy months or years of labor. Tool wear mattered. Abrasive quality mattered. Transport risk mattered. The system succeeded not because the Egyptians possessed perfect control, but because they developed methods resilient enough to work often enough. Failure was part of the technological landscape. That makes the surviving successes even more impressive, not less. If there is one sentence that captures the real story, it is this. The Egyptians did not so much cut granite in the modern sense as they pounded it, abraded it, drilled it, and wore it into obedience. Modern language can mislead us because cutting sounds like a single act done by a sharp edge. Egyptian granite. Working was usually a chain of acts performed by different tools on different scales. The edge might be blunt, the motion might be repetitive rather than forceful. The abrasive might be doing more work than the tool body. Once you shift your imagination from slicing to grinding, the evidence clicks into place. So when people ask what the hieroglyphs reveal, the best answer is that the inscriptions and scenes reveal the world around the granite, the crews, the officials, the workshops, the transport, the ideological importance of monument making. The quarries reveal the rough method. The drill cores and saw marks reveal the finer method. And taken together, they point not to some vanished machine age, but to a civilization that mastered stone through an intelligent marriage of labor and materials. And when people ask which tool they relied on, the answer depends on which stage you mean. For quarrying and roughing out the giant mass, the unglamorous hero is the dolerite pounder. For precise linear cuts and holes, copper saws and tubular drills carrying abrasive were indispensable. For finishing, rubbing stones and fine abrasive pastes completed the job. But if you strip the system down to the tool that made granite quarrying possible at its most fundamental level, the evidence leads back again and again to the tough, dark hammerstone striking bedrock in the Aswan sun. That should change the way we look at Egyptian technology. We often rank civilizations by how closely they resemble us, how much steel they had, how much mechanization they used, how much energy they could concentrate into one machine. Egypt's granite work follows another logic. It shows how much can be achieved when a society understands materials deeply enough to compensate for the limits of its metals. It shows that technology is not just what a tool is made of. It is also how many stages a process contains, how well labor is organized, and how cleverly natural substances like sand can be turned into precision instruments. In the end, the granite monuments of ancient Egypt are not evidence of a missing chapter in history. They are evidence that we underestimate ancient people whenever we confuse simplicity with weakness. A stone hammer can be a high technology in the right system. A soft copper blade can become lethal to granite when loaded with the right abrasive. A painted tomb wall can preserve the social anatomy of production even when it leaves out the finer mechanics. And a scarred quarry floor can tell the truth more clearly than 1,000 modern fantasies. So the next time you see a granite obelisk, a royal statue, or a polished sarcophagus and wonder what impossible machine made it, picture something far more real. Men in a quarry striking bedrock with dolerite pounders, teams dragging stone under official supervision, craftsmen feeding abrasive sand into copper saw cuts, drillers rotating tubular tools into hard stone, and finishers rubbing surfaces smooth until the monument looked eternal. That is how the Egyptians really did it. Not with magic, not with myths, with stone, sand, copper, sweat, and time. If you want more deeply researched scripts that separate real ancient engineering from modern legend, subscribe, leave a comment with the next mystery you want unpacked, and share this video with someone who still thinks granite proves the Egyptians had power tools. This script was based primarily on archaeological and museum evidence from the Aswan Quarry Survey, the Met's research on ancient Egyptian stone-cutting technology, Penn Museum's study of Egyptian stone drilling, PBS Nova's documentation of experimental granite cutting with sand, Dennis Stock's experimental stoneworking research, and contextual material on Egyptian workshop imagery and hard stone finishing methods.